Thank you for tuning in to my talk today about ihi Seamount, which is the youngest volcano of the Hawaiian island chain. My name is Thi Truong, and I'm presenting research that I have done with my collaborators, David Graham, Mike Garcia, and Peter Michael. To study ihi, we must start with Hawaii. If we orient ourselves on the south coast of Hawaii and move offshore about 30 kilometers, we will see an underwater volcano at about 1 kilometer below the sea surface. This is ihi Seamount. It is a young volcano with 2 rift zones which developed early in its history. Ihi has erupted a diversity of lava types despite its short life. For these reasons, ihi has transformed our understanding of the earliest stage of Hawaiian volcanism, called the pre-shield stage. In addition, the presence of tholeiitic basalt flows indicate that a shield transition has already occurred or is ongoing. Shown here is a summary of the methodological approach to collect basaltic glasses for geochemical analyses. Shown on the right is a 3D scan showing the interior of a glass chip where vesicles or vapor bubbles are visible. These types of bubbles are mostly composed of CO2, and they are likely to host the majority of helium as well. Early noble gas studies at ihi have established that ihi has among the highest helium isotope values at a Hawaiian volcano. This helium isotope value is believed to arise from the primordial mantle input, that is, a deep mantle source which has retained chemical characteristics of an early Earth. At the same time, significant variation in helium isotopes results in values as low as 20 Ra, producing over 10 Ra difference of helium isotope values. Because ihi is close to the hypothesized melting region of the Hawaiian plume, its variation sheds light not only on the lesser understood pre-shield stage, but on the present-day distribution of chemical heterogeneities sampled by the Hawaiian plume. Some explanations for the lower helium isotope values at ihi include intrinsic variation within the plume, radiogenic ingrowth of uranium and thorium, as well as atmospheric and seawater contamination. The addition of recycled components, such as subducted crustal materials, may also account for this signature. Integrating helium, carbon, and water measurements of quenched basaltic glass can be used to explore this hypothesis. However, most previous studies at ihi have focused on the shallow summit region, where the retention of volatiles from the mantle is a concern. An expanded study of ihi's deeply erupted glasses is needed. The objective of this study is to contribute a comprehensive data set of coupled volatile measurements from over 40 basaltic glasses collected from ihi's deep rift zone. Basaltic glasses were chosen because they represent erupted melt compositions. Collection depths from 1,300 to 5,000 meters beneath sea level means that samples were erupted under relatively high confining pressure. In contrast to the shallow summit, where gas loss is expected to be more extensive, high pressure from the overlying water column in the deep rift should promote the retention of magmatic volatiles. The majority of samples from ihi with published helium isotope data do not have values determined by both crushing and melting. In this study, helium and CO2 contents were measured from both the melt and vesicle components to compute total contents, which were used to evaluate relative behavior and partitioning. Water and trace element compositions were measured on the melt components. This dataset provides a means to evaluate the causes of volatile and helium isotope variation at ihi Seamount. For the rest of this talk, I will be presenting results that address the following questions. Is there systematic variation in helium isotopes at ihi? Are CO2 and water contents heavily modified by degassing? Does elevated CO2 over helium-3 reflect the addition of recycled materials? And do trace element signatures support the addition of recycled materials? Local variation at a single volcano will be useful to apply to the broader scale, say of the Hawaiian Islands or the global high helium-3, helium-4 reservoir in the deep mantle. For the rest of this talk, I will be using the same color coding to indicate composition within the sample suite. These designations are based on the normalized major element composition of each glass relative to its position along the MacDonald-Katsura line and based on alkalinity index. Within the south rift zone of ihi, alkali basalts are shown in yellow, transitional basalts are shown in cyan or light blue, and tholeiites are shown in red. In the North Rift zone, 3 samples from the same dredge are tholeiites. These are shown in orange. Helium isotope values are within the range of previous studies. If we focus in on the results of the South Rift, we see that mean helium-3, helium-4 values for tholeiites and transitional basalts are different. Specifically, tholeiites are higher than transitional basalts. They are different despite the fact that they often have overlapping values. This study does establish that the diversity of rock types can be related to the diversity of helium isotope variation. It is also notable that the North Rift tholeiites in the study are higher in helium-3 compared to the South Rift tholeiites. Moving on to carbon and water results, we see CO2 measurements vary greatly among Lōʻihi deep rift samples. Comparing CO2 to a trace element like barium indicates that samples have degassed by 95 to 99%. That is, the least degassed samples have lost at least 95% of their original carbon inventory. Lōʻihi samples are highly degassed despite erupting at great depths. However, water-potassium ratios suggest that dehydration has not occurred. Multi-species element modeling with carbon and water indicate that the least degassed samples correspond to about 2.3 kilometers equilibration depth. To evaluate the extent of vapor melt partitioning at Lōʻihi, we examined the CO2 and helium concentrations in the vesicles and the melt. All of Lōʻihi samples plot outside the equilibrium field as indicated by Henry's law. Vesicle melt partitioning suggests that helium diffuses faster into bubbles than CO2. Another way to evaluate this equilibrium is to look at the CO2 over helium-3 ratio. This ratio is said to be consistent across mid-ocean ridge and ocean island basalt sources. Deviation from canonical mantle ratios indicate potential recycling processes. In our Lōʻihi suite, we do see some elevated CO2 over helium-3. This might indicate recycled input due to elevated CO2. However, our examination of vesicle melt partitioning indicates that non-equilibrium or kinetic degassing is likely to have occurred. Combining our results from vesicle melt partitioning and the CO2 over helium-3 ratio suggests that preferential loss of bubbles has led to the loss of helium-3. This bubble loss will then drive the CO2 over helium-3 ratio upwards. Hence, the CO2 over helium-3 ratio may not reflect the source or recycled components. Instead, it reflects disequilibrium degassing processes. While integrated helium-carbon results may not support recycled components in the Lōʻihi source, some trace elements are indicators of possible recycled material. For example, we see slight positive anomalies in niobium and tantalum. Lōʻihi is notable for its elevated niobium anomalies, both in previous studies and this current study. Elevated niobium has been attributed to recycled crustal materials, for example, eclogite in the mantle. In addition, niobium over uranium ratios, which are typically consistent across OIB and MORB, are actually elevated in Lōʻihi. This indicates the possible enrichment from recycled materials. In conclusion, this study yielded a number of results related to volatiles at Lōʻihi. Helium systematically varies between rock types within the South Rift. Furthermore, the North Rift tholeiites samples have among the highest helium-3, helium-4 measured for this whole dataset. This suggests some spatial variability, at least in helium isotope ratios, between the North and the South Rift. Another major result is that carbon contents vary widely at Lōʻihi, and this is due to variable degassing of at least 95% of the least degassed sample. Despite the loss of carbon, water loss has not occurred. Integrated helium and carbon results indicate that preferential loss of helium may occur by bubble loss and non-equilibrium or kinetic degassing. In addition, trace element signatures may support the existence of recycled materials. Trace element results indicate that high helium-3, helium-4 samples also have positive niobium anomalies. This supports the existence of recycled materials with primordial material. The trace element signature of niobium over uranium at Lōʻihi is elevated compared to global ocean island and MORB sources. This suggests the addition of enriched or altered material. Overall, this study sought to incorporate volatile measurements and trace elements of a diverse set of lavas from the ihi Seamount to constrain primordial and recycled components in the mantle source. I hope this talk has convinced you that local variation at a single volcano can be used to understand broader scale processes happening in the global mantle. Thank you for watching my talk. I also want to thank my collaborators, and I want to thank the session conveners, Val Finlayson, James Doughton, and Gibran Labidi, for inviting me to give this talk. Thank you to everyone who made this work possible, and I look forward to seeing you in the live session on Tuesday, December 14th.